Yeah, okay. So our next speaker is Davide Trotta from Pisa.
Thank you very much. I'm very glad to be here today and to present this talk, which is based on a recent work, which is joint work with Maria Emilia Maietti. And well, the main purpose of this talk is to present a characterization for two free constructions, which are the regular and exact completion of Lovier doctrines. And in order to give you an intuition of what these two free constructions are, and in order to explain what is what are our main motivations and what is the main goal of this talk, I would like to start this talk by recalling two particular instances of these two constructions for doctrines and presenting a characterization for these two particular instances. And well, the particular instances here are the so-called regular completion of a category with finite limits and the exact completion of a category with finite limits. These two constructions are well known in category theory and categorical logic. The first one takes a category, a lex category, so a category with finite limits, and produces a regular category, while the second one produces an exact category from a category with finite limits. And for these two free constructions, we have the following characterization. And here also it is important to understand what kind of characterization we want to achieve for Lovier doctrines and the exact completion, regular completion of these doctrines. And well, the kind of characterization that we want to generalize are these two characterization for the regular and exact completion of a lex category. The first characterization says that essentially a category which is regular is an instance of the regular completion if and only if the subcategory of its regular projectives object is closed under finite limits. The category has enough projectives, which means that every object of the regular category can be covered by a regular projective. And every object of the category is a sub-object, essentially. It can be embedded in a regular projective object. So this is the first characterization. These are the properties that a category, a regular category, has to satisfy in order to be an instance of the regular completion. And in this case, it is precisely the regular completion of if it's a subcategory of regular projectives. And similarly, we have a characterization for the exact completion. In this case, we have that an exact category is an instance of the exact completion, so it can be obtained as the result of this completion, if and only if the subcategory again is closed under finite limits and the category has enough projective objects. You can find this at the bottom of the slides. There are some references. For example, you can find these two a characterization in this paper by Carboni. And well, these are the two characterizations that we know for the regular exact completion. Since Maietti and Rosolini proved that these two free constructions are particular cases of more general constructions for Lovier doctrines, we want to extend this characterization to generalize this characterization for Lovier doctrines. In particular, we want to present a notion in the language, for example, of Lovier doctrines, that of element which will play the role of regular projective object in a regular category, and so on, and to present a characterization of this kind. So this is the main goal, presenting a characterization of this shape for exact and regular completion of Lovier doctrines. So we can start now with all the details. And first of all, I want to fix the notation. So I want to recall what are the doctrines that I will use today. And today we will work with a generalization of the original notion of Lovier hyperdoctrine. Here you can find a very simple generalization. A primary doctrine is simply a functor from the opposite of a category with finite products into the category of insemi-lattices. So this is a primary doctrine. Now, a primary doctrine is said to be existential if for every pair of objects, A and B of the base category, and any projection, this functor, which is, I'm using this notation to denote the functor obtained by applying the doctrine, so this functor on this projection. So this functor has a left adjoint denoted in this way, and this satisfies two conditions, which are the Beck-Chevalier condition and the Frobenius reciprocity. The intuition is that an existential doctrine is a doctrine which, while it has enough structure to properly deal with the existential quantifiers in logic, and these two conditions are two technical conditions, which basically means, for example, Beck-Chevalier, it says that an existential quantifier commutes properly with the substitution. This is the intuition. And now we have that a primary doctrine is elementary if the idea is that it is able to model the equality. So if formally we can say that a doctrine is elementary, if for every object A, there exists an object of this fiber, which is essentially an equality predicate. So this is the idea. This is a generalization of the concept of equality predicate. Such that these two conditions are satisfied. This is essentially, this says, the first condition says that we can define a left adjoint along this functor where this is the diagonal, and similarly we can define left adjoints for all the functor obtained in a similar way, so along morphisms of the form identity times diagonal. So the crucial point is that an elementary doctrine is a doctrine where we can use to properly deal with the equality in logic. But now we can see some examples. The first one is the syntactic doctrine. In this case, we can consider the so-called regular fragment of first-order logic. So it is the fragment built on this with the top, the conjunction, the equality, and the existential quantifiers, for example. And we can consider a theory in such a fragment. Then we can define the syntactic doctrine, that is a functor from a category, which is essentially the objects of this category are contexts, and the morphisms are essentially substitution. And every context, and if consideration is the name similatism whose elements are predicates in such a context, and the order is given by the probability. So we will see that a formula is less or equal to another formula if, assuming the first, we can prove the second one, for example. And of course, this doctrine is elementary and existential because we can define, for example, the left adjoint functors along projection using the real, let me say, real existential quantifier from the logic, and similarly, we can use the equality to define the elementary structure of the doctrine. Now there are other two known examples of elementary and existential doctrines. The first one is the case of the so-called weak subobject doctrine. In this case, we can consider a category with finite limits, and weak objects or also variations. In this way, for every object...
Sorry. Can I interrupt you for a second? Is David's screen freezing for anyone besides me? Yeah. Okay. I think it'll be better if you turn off your camera.
Okay. Let me.
Okay. Sorry to interrupt.
Do you sides? Do you hear me?
Yeah. Yeah. Go ahead.
Okay. So I was presenting this weak subobject doctrine. So this is a functor that takes an object of the base, and essentially this is the poset obtained by the poset reflection of the slice category on this object. So an element of this poset is simply an arrow whose codomain is this object, and this doctrine is elementary and existential. Similarly, we can consider another doctrine, which is the subobject given by the subobject functor. In this case, we can consider a category with finite limits. And in this case, if we take the subobject functor, this doctrine in general is not elementary and existential, but it is both elementary and existential if and only if the category is regular, because we need essentially a factorization system to define the left adjoints along projections, so the existential quantifiers. This is the idea. This is, if we have a category with finite limits, this is elementary, but for obtaining elementary and existential doctrine, we need to require that the base category is regular. Okay, now some other examples of doctrines which will be used later. And well, a doctrine, essentially, we can consider a doctrine which is elementary and existential, and we say that this doctrine is equipped with the Hilbert epsilon-operator, essentially, if every existential quantifier can be presented admits a witness function in some sense. In a formal way, we can say that if we have an object of this category, we say that this object is equipped with Hilbert epsilon operator if for every object of this, for every other object of the category and every element of this fiber, there exists a witness function such that this existential quantifier, so we can apply the existential quantifier along a projection on this object. This can be written in this way, so we can delete the existential quantifier and using this essentially this witness function. This is the idea. And well, a doctrine such that every object has this property is said to be a doctrine equipped with the Hilbert epsilon operators. So this is a very particular family of elementary and existential doctrines, because every existential quantifier can be presented in this way with such a witness function. Now, I want just to conclude this first part about doctrines by quickly recall the two categorical structure for the category of primary and elementary and existential doctrines. So we can formally define the notion of morphism between two doctrines. So we can define, for example, a one cell as a pair of where the first component is a functor from this category to this one, preserving finite products. And the second component is a natural transformation from the first doctrine into to this functor. And we can define the two cells in this way. A two cell is a natural transformation from the first component of a one cell into the first component of another one cell, such that this condition is satisfied. So primary doctrines with these one cells and these two cells form a two category that we will denote in this way. Similarly, we can define the subcategory, the two full subcategory of elementary doctrines and of elementary and existential doctrines, for example, in a similar way. So we need to require, for example, that the one cells commutes properly with existential quantifiers, or that the one cells preserve the equality predicates, for example. But this just for fixed denotation, we have the two category of primary doctrines, the two category of elementary doctrines, and the two category of elementary and existential doctrines. Now I want to introduce a notion in the language of Louvier doctrines, of elementary and existential doctrines, that will play the role of regular projective in the regular completion. So this is the first step that we want to address. We need to define a notion in this language of doctrines for that will become later the projective object in the regular completion. So let us consider an existential doctrine. we say that an object alpha of a given fiber is said to be an existential splitting if whenever alpha is equal to an existential quantifier along a projection of another object beta, then there exists an arrow, age, such that alpha is equal to this object. So alpha is existential splitting if whenever it can be written as an existential quantifier, we can find a witness function such that this equality exists. So we can always find a witness function for an existential quantifier such that this is equal to alpha. And the fact is that this property in general is not stable under reindexing. This means that if alpha is existential splitting, if we apply substitution, what we obtain is a new object, but in general is not an existential splitting. An existential splitting such that every reindexing remains existential splitting is said to be existential free. So an object of a doctrine is existential free if for every morphism, this is again an existential splitting. Whenever we apply this function, we obtain again an existential splitting. Now, we want to use this kind of object to define the notion of existential cover for a doctrine. Just to give you an idea, we will see later that the notion of existential free element, for example, in the case of the syntactic doctrine associated with the regular fragment of Sturder logic, coincides with the syntactic notion of existential free element. So there is a tight these two notions are very connected in this sense. In the particular case of the syntactic doctrine, being existential free in the previous sense coincide with being existential free in the syntactic sense. Now, given an existential doctrine, we simply say that an element alpha is covered by an element beta of this fiber if alpha can be written as an existential quantifier of beta. This is just to fix the notation. Now, we say that a doctrine, an existential doctrine, has enough existential free object if every object alpha is covered by some existential free element beta. So, for every object alpha, we can find an existential free element such that alpha can be written as an existential quantifier of beta. And this, again, reminds the notion of having enough regular projectives in the language of regular categories. And now we are ready for presenting the main results, but again, we need to introduce a last notion. We will say that an existential doctrine, so we can consider an existential doctrine and a full subdoctrine. We say that the full subdoctrine is an existential cover of this doctrine. So now we have two doctrines. We will say that the first one is an existential cover of this one if every element of this subdoctrine is existential splitting and hence existential free. And every element alpha is covered by an element of this subdoctrine. First property, if we have a doctrine, an existential doctrine, and a full subdoctrine, if this full subdoctrine is an existential cover of the doctrine P, then the existential free elements of the doctrine P coincide exactly with the elements of P prime. Therefore, if an existential cover exists, it is unique. Now, using these notions, we can provide a characterization of doctrines having the property of being existential completions, in the sense that we can formally, there is a free construction that formally adds existential quantifiers to a given doctrine, that takes a doctrine and produces an existential doctrine, and we can formally characterize this doctrine the doctrine are raising as instances of this free construction, which freely adds left adjoints, using this notion of having existential covers and or existential free elements and so on. And the characterization is this one. We can consider an existential doctrine, and we have that the following 3 points are equivalent. The first one says that P has the universal property of being an existential completion of a primary doctrine P prime. Then P satisfies the following points. It satisfies the rule of choice, which means that every top element is existential free. The existential free elements are closed under binary conjunctions. Again, from a syntactic point of view, this is quite natural if we have two predicates which are existential free, their conjunction is still existential free. And finally, we require that P has enough existential free elements. And the last condition is P has a unique existential cover. So it has an existential cover, and because of the previous lemma, we know that it is unique. So these three, this essentially characterize which are these frequencies which have an existential cover. Application of this as a corollary would obtain, for example, that every elementary and existential doctrine is equipped with Hilbert epsilon-operator if and only if it provides an existential cover of itself. Now I want to show how we can apply this notion to characterize the regular and exact completions. And for this reason, I need to quickly recall what are these free construction for doctrines. Again, I don't want to spend much time in recalling all the details, but I want just to recall the main properties of these constructions. And well, the fact is that if we have an elementary and existential doctrine, we can define a regular category. In this way, the idea is that the objects of this regular category are pairs where the first component is an object of the base and the second one an object of this fiber. And an arrow from an object of this kind to an object of this kind is given by an element of this fiber given by the product of these two objects, which is essentially entire and functional with respect to these elements. So which means that, for example, this means that these two conditions, for example, means that it is entire and functional, and this that it is well defined on these two formula. But again, I don't want to recall all the detail. I want just to give a quick intuition of what is this regular category. And of course, we have that this construction can be formally defined, and it provides a two-functor from the two category of elementary and existential doctrines into the two category of regular categories. And this is a left B adjoint to the inclusion functor from the two category of regular categories into the two category of elementary and existential doctrines, which takes essentially a regular category and produce and sends it to the subobject functor on this category. Some examples. These are results that you can find in a series of papers by Maietti and Rosolini, for example. And this is essentially the reason why we can say that the regular completion of doctrines, for example, generalizes the regular completion of a category with finite limits. This because if we apply the regular completion to the weak subobject doctrine, what we obtain is precisely the regular completion of this category, which is a lex category. And so we can present the ordinary regular completion as a particular instance of the regular completion of elementary and existential doctrine. Now, if we apply the regular completion to the syntactic doctrine, what we obtain is precisely the syntactic category that is denoted in this way in the book of Johnstone, Sketches of an Elephant. So this construction applied to the syntactic case provides exactly the so-called syntactic regular category associated with this theory in this fragment, for example. Now, as I said before, we want to understand what is the correspondence between existential splitting elements and regular projectives. And in this result, we explain precisely this. So we have an elementary and existential doctrine, then an object of this regular category, so in the regular completion, is if this formula is an existential splitting, then this object is a regular projective. Moreover, we have that if this doctrine has enough existential free objects, then every object of this regular completion is covered by a regular projective object. You can find all the details in this preprint. And now we can use this result to characterize to present our main characterization. I just need to introduce a particular category. This is a little bit technical, but it is necessary to present a final characterization of the regular completion of a doctrine. And for this reason, I need to recall what is the category of predicates associated with an elementary doctrine. In this case, we have that given an elementary doctrine, we can define again a new category whose objects are again pairs, where the first component is an object of the base, and the second component is an element of this fiber. And arrows are equivalent classes of arrows of the base, satisfying this condition. And the equivalence relation is this one. We will say that two arrows of the base category are satisfy this relation when we apply this pair to the quality predicate, we obtain the top element, essentially. And again, this category is useful, and we can define the so-called graph functor from essentially the category of predicates associated with a given subdoctrine of an elementary and existential doctrine into the regular completion of this doctrine. I don't want to recall all the detail. I want just to say that if we have a doctrine and an elementary subdoctrine, we can define a graph functor from the category of predicates associated with this subdoctrine into the regular completion. And then what we have is that such a graph functor is an equivalence if and only if this doctrine has an existential cover here. So this is the characterization. We have that if we consider an elementary and existential doctrine, this doctrine admits an existential cover if and only if this graph functor provides an equivalence for the regular completion and the regular completion of this category. So this is the regular completion of the doctrine. This is the regular completion of this lex category. And similarly, we can extend this characterization for the exact completion. This because we know that if we have an elementary and existential doctrine, the exact completion of this doctrine can be presented in this way in terms of regular completion and exact completion of a regular category. So the exact completion of an elementary and existential doctrine is given by the exact completion of the regular completion of this doctrine. So this is the X-reg completion, and this is the regular completion of the doctrine. And again, this assignment extend to a two-functor from the two category of elementary and existential doctrine into the two category of exact categories, which is left be adjoint to the inclusion. So here there are some examples. I think that I have not time to present all the detail now, but I want just to recall that this exact completion again is a generalization of the ordinary case of the exact completion of a Lex category, because when we apply the exact completion to the weak subobject doctrine, we obtain precisely the exact completion of this category. And in the syntactic case, we have that the exact completion of the applied to the syntactic doctrine provides exactly the effectivization of the syntactic category associated to this theory. And this is denoted again in the book of Johnstone in this way. And when we apply this exact completion to the subobject doctrine, we obtain in this case the exact completion of the regular category given by the base. So these are other examples of category obtained in this way. And as a direct corollary of our previous result, we obtain that doctrine, which is elementary and existential, as an existential cover if and only if the graph functor provides an equivalence from this exact category and this category, which is obtained by the exact completion of the category of predicates of P prime, which is a Lex category. And here there are some corollaries. For example, we obtain again the characterization presented by Maietti and Rosolini Pasquali in a previous paper of the exact and regular completions of doctrines equipped with the Hilbert epsilon-operators, and this is the essentially this is the characterization. We have that the doctrine is equipped with Hilbert epsilon-operators if and only if the graph functor from the regular completion into this regular category is an equivalence, if and only if this again gives an equivalence between the exact completion of the doctrine and the exact completion of this Lex category. Again, notice that here we have the doctrine itself, because we proved before that a doctrine is equipped with the Hilbert epsilon-operators if and only if it is an existential cover of itself. So this is again can be obtained as a particular case of our characterization. And finally, here there are other two applications, but I want just to mention them without providing the detail. We have that, for example, the Joyal's arithmetic universes can be obtained by combining the exact completion of a doctrine with the existential completion of an elementary and existential doctrine. And using this free construction, we can define a sort of categorification. We can extend essentially the elementary doctrine given by the primitive recursive predicates into another one which is existential. And finally, we have again the application in the syntactic case, so we can consider the regular theory given essentially the initial regular theory in the regular fragment of first order logic. In this case, we have that the syntactic doctrine associated with this regular fragment essentially is the existential completion of the syntactic doctrine associated with the Horn fragment of first order logic, and therefore we have that this syntactic category can be presented as a regular completion of the category of predicates associated to the syntactic doctrine given by the Horn fragment of first order logic. And then we obtain also the characterization for the effectivization of this category. And I think that I have to stop here. In these slides, there are some references for where you can find these results. So thank you very much for your attention.